Hi Guy, I'm Laurie from AI Elephant.
Hi guys, I'm Leo.
We often say that AI needs to be smart like a super brain. But have you ever wondered, are the training goals for a smart AI and a reliable AI exactly the same?
That is a tricky question. For us regular users, if an AI can answer my questions, make the conversation flow smoothly, and write a decent piece of copy, I already think it is very smart and reliable. Is there really a fundamental difference between the two?
The difference is significant. It is like the difference between a high EQ chatbot, who is witty in a chat room, and a surgeon who can perform a highly complex operation precisely. In this episode, we're going to dive into how the latest research from UC Berkeley argues that to upgrade from an excellent chatbot to a highly reliable engineer, we must pivot to a completely new domain, post-training verifiable agents. In the era of traditional LLMs, like the familiar chatbots, their core goal was to maximize human preference through reinforced learning from human feedback, RLHF. Simply put, the model needed to make you feel good with engaging and empathetic responses.
Right? High emotional intelligence. But what is wrong with that? Don't we want AI with high EQ?
Of course we do. But when executing a task, high EQ alone cannot guarantee correctness. Traditional LMs are evaluated by ranking human preferences to build a reward model, which is suitable for not verifiable dialogue tasks. But the emergence of modern agentic models has fundamentally changed the objective. Agentic models are no longer content with being a high EQ chatbot. Their goal is to accomplish actual tasks, for example, booking a flight that meets a specific date and budget, or fixing a complex code bug. At this point, they must maximize verifiable rewards, which means maximizing correctness.
I see before, it was sound good is enough. Now it is the answer must be right. For a math problem, the agent must call a Python code tool to ensure the calculation is flawless, rather than giving me a solution that just sounds plausible. If the answer is wrong in an enterprise application, it could mean a failed booking or even a system crash. The pressure is totally different.
Exactly. The agent must interact deeply with the real environments, be it a code repository, a software system, or various tools. It must be able to produce an explicit, clear verifier that can prove the correctness of its answer. This is a fundamental leap from a liberal arts major to a science and engineering professional. To successfully build this highly reliable verifiable agent, we need to focus on solving three core challenges. The speaker compares them to the tripod supporting system: reliability, data, evaluation, and training.
Data evaluation, training. It sounds much like how humans learn. We acquire knowledge, data, take exams, evaluation, and improve through practice, training. So, what are the challenges in the AI world? Is it just a mechanical copy of the human learning process?
Far from it. Translating the natural feedback loop of human learning into algorithmically implementable steps is precisely the most complex and challenging part of these three phases. Let's start by delving into the foundation: data. Data is the bedrock of the agent, but good data here has extremely high requirements. It must ensure comprehensive coverage across sufficiently diverse environments, callable tools, and, most critically, diverse verifiers.
I understand environments and tools. They are the scenarios the agent operates in, like a coding environment, enterprise database, or an API interface. But why is the verifier so crucial? Isn't it just a simple right or wrong judgment?
If you only view it as a simple yes and no judgment, you easily fall into a huge trap. The speaker emphasizes that the verifier should not be a single judgment, but a vector that assesses the model's quality from multiple perspectives. For example, a simple change-making problem might require the answer to be in the simplest form. If your verifier only checks if the final number is correct, but fails to capture the nuance of simplest form, it will mistakenly reward a redundant or inefficient answer.
Wow! That is like when I did math problems as a kid, even if the final answer was right. If the steps were too complicated, the teacher still deducted points. So, if the verifier doesn't capture the subtle difference between correct and excellent, the AI will never get the right training signal and can't learn to be a truly good engineer. Is writing this kind of high-quality, nuanced verifier extremely difficult?
It is widely recognized as a major challenge in the community. We must minimize false positive and false negative errors. Any error could lead the agent to make a catastrophic decision at a crucial moment. High-quality data must holistically and accurately construct the environments, tools, and these multidimensional verifiers. With data in place, the next step is evaluation. The core role of evaluation is to ensure the agent's generalizability, its ability to operate in unseen scenarios, with new tool configurations, and in diverse environments. The greatest risk is falling into an illusion.
What does illusion refer to? Is it like studying for an exam by only doing one mock test, and then completely freezing up when the actual exam has a different format?
Yes, that is overfitting. By only testing the parts that are highly aligned with the training data, you get a high score and mistakenly believe the model is powerful. A truly good evaluation system must test the model's compatibility across different software systems, and especially its performance when human instructions are vaguely specified.
The point about vague instructions is particularly interesting. A mature engineer doesn't immediately start working on a vague request. They proactively seek clarification. Therefore, a high-level agent also needs this ability for proactive interaction to debug and clarify user intent. That is true robustness. Just being able to answer questions is not enough.
Precisely. To achieve this, the academic community has developed a series of benchmarks, such as SWE-bench and ToolBench. These benchmarks require the agent to solve the same tasks across different tool harnesses or API configurations, thereby proving that its intelligence has reached the threshold of being able to abstract the essence of the task. However, the evaluation system itself faces a credibility challenge. When all models can easily achieve high scores on a benchmark, that benchmark loses its discriminative power. We cannot be fooled by leaderboard numbers.
Wait, isn't that a good thing? Everyone scoring high means AI is improving overall, right? Are we hoping the AI gets dumber?
We want the AI to genuinely improve, not just learn to overfit the benchmark. Therefore, we must continuously monitor three aspects to maintain benchmark credibility: hardness, separability, and diversity. Hardness must keep pace with model improvements. Separability must effectively distinguish between the capabilities of strong and weak models. And diversity must ensure the benchmark has sufficient coverage, preventing models from looking good by only scoring high on a small set of prompts. Benchmarks are tools to drive community progress, not just for scoring points. With data and evaluation addressed, we move into the third core step, training algorithms. The current mainstream training paradigm is two-stage. First, super fine-tuning SFT, followed by reinforcement learning RL.
My understanding is that SFT is imitation learning, getting the AI to learn the homework first and avoid major detours. RL is the real exploration, reinforcing its abilities through trial and error, right?
That is very accurate. SFT aims to imitate the correct demonstration trajectories, serving as a jump start for the system, avoiding a large number of costly, meaningless attempts early on. RL is the key to true intelligence, using self-exploration to reinforce correct and diverse trajectories and discourage incorrect attempts. Diversity is the soul that accelerates learning here. In the RL phase, there is an extremely dangerous spell entropy collapse. This refers to the phenomenon where, as model performance improves, its generation entropy actually decreases.
Entropy collapse sounds very abstract. Can you explain in layman's terms how this relates to training AI?
In simple terms, entropy is the model's uncertainty about the next possible token or action to generate. Entropy collapse means the model becomes overly confident that its current answer is correct, leading it to generate only one single answer. This causes it to stop exploring and stop generating diverse correct or incorrect answers. Once entropy collapse occurs, the system's ultimate intelligence will hit a plateau. The core idea to solve it is to force the model to explore. For example, by decoupling clipping thresholds in algorithms to encourage the model to increase the probability of low probability tokens, or by directly adding an entropy loss to maintain a high level of generation entropy.
So, training an AI is like nurturing a super genius. We don't want them to become complacent, only trusting their existing set of problem-solving methods. We have to keep pushing them to stay humble and maintain their curiosity. Besides training for longer to prevent complacency, what other strategies are there to make them train harder and sample better?
There are many strategies. For train on more difficult prompts, we need to mix tasks of varying difficulty in the training set and adjust rewards based on the sample's difficulty, giving the model more confidence in high difficulty tasks. For sample better, there is a cool technique called parallel reasoning, which asks the model to generate multiple, e.g. 32, different answers simultaneously, and then select the optimal one. There is also the deep confa technique that tracks trajectory confidence, which can exclude or low-weight those outputs with extremely low confidence and poor quality. All these efforts are ultimately aimed at allowing the agent to better mimic humans, receiving feedback after making a mistake, and ensuring that the quality of the next attempt is truly improved. Reflecting on our discussion of verifiable agents today, we can say that this field is still in its infancy, but the direction is very clear. We can propose 3 summary recommendations today. 1. Shift the mindset from preference first to verifier first. Treat the verifier as a multi-dimensional vector for assessing the model rather than a simple right or wrong judgment, capturing all the nuances. 2. Focus evaluation on generalizability. Continuously invest resources to create and maintain public benchmarks that excel in hardness, separability, and diversity, preventing the illusion of overfitting. 3. Concentrate training algorithms on exploration reinforcement. The entropy collapse spell must be broken. Strategies like parallel reasoning must be used to encourage the generation of diverse attempts, which is essential for sustaining the agent's generalization and evolution.
After today's discussion, I feel that what we are doing is striving to bridge the gap between human learning and system learning. Training a verifiable agent is like raising a truly senior engineer. We require them to be not only technically superb, but also trustworthy and capable of autonomously learning from mistakes. Thank you, Larry. For the deep analysis today, we hope this has been enlightening for our listeners.